Okay, I think it's 10:05, so I think you can start. So yeah, let me stop sharing. Okay, you can try to share your screen.
Sounds good. Thank you. See,
Mm.
can you see my screen now?
Yes, we can see.
Okay, awesome.
Yeah, sorry, by the way, for those who have Q&A during any questions during this presentation, this tutorial session, please drop your Q&A in the Q&A section below. Then later we will answer some of your questions at the end of the tutorial session. Thanks. Okay, you can continue. Thanks.
Okay, thank you for the invitation, and also thank you for organizing this event. My name is Kai Wang from Harvard University. I'm currently a fifth-year PhD student in computer science department. And today I'm going to share about my research, which is about decision-focused learning. I'm sure you might not hear this idea before, but I'm gonna introduce that to you. And the main idea is to integrate optimization problem into machine learning or training pipeline to resolve not only social challenges, but also some other kind of industry challenges. Yeah. Right. So before we go into the technical details, so we can first look at or review what's the use of artificial intelligence in social challenges first. And in particular, I'm focusing on two specific social challenges. One is wildlife conservation. How do we use artificial intelligence to determine where to patrol the national park in order to save more wildlife? And second one is healthcare program. So how to use artificial intelligence to recommend, for example, like healthcare worker to visit some patients or some potential beneficiaries in order to improve the overall performance of the healthcare program. And we have seen many use of artificial intelligence in this challenge, in particular, wildlife conservation. Like I said, people have been using technologies to predict where with poaching hotspots, and therefore use those predictions to determine where to assign patrol to patrol the entire national parks. In the healthcare domain, we are also working with a non-government organization, ARMN, in India, to use technology or use artificial intelligence to determine where should we recommend healthcare workers to visit those potential models or patients in order to improve the overall healthcare quality. And the overall question is how artificial intelligence can help in these social challenges. And I'm gonna divide the role of artificial intelligence into three parts. The first one is learning, and the second one is planning, and the last one is deployment. And learning, planning, and deployment can be split into this, can be integrated into this pipeline, where learning is trying to use the features in the social challenges. So for example, in the national park, we might have some features of each individual locations. We can use those features to predict what's the poaching risk or poaching probability in that particular location. And therefore, what we're gonna do here is to learn a predictive model using any kind of learning method, using any kind of machine learning to maximize the predictive accuracy. And therefore, we can know where the poaching hotspot will be. And next, the planning component is gonna take over the prediction that we just made, where the poaching hotspot is, and then later determine where should we allocate limited resources, limited human resources, or limited patrol resources to patrol the entire national park to improve the healthcare quality in the healthcare program. And that's one is the deployment. So once we figure out what's the decision, what's the optimal solution to the social challenges, we can try to deploy this solution to actually translate the algorithm or algorithm solution to social impact. So these three are the three main components in AI for social impact or AI for social challenges. But as we can see that these three, in particular, the first two, more related to artificial intelligence or machine learning, they are actually trying to optimize different goals, or trying to optimize different objectives. In particular, for the learning component, what we want to do is to maximize the predictive accuracy. In the planning component, instead, what we're gonna do is to maximize the decision quality. Apparently, these two are different. So the main idea of my research, which is decision focusing, is trying to mitigate these two, the mismatch between these two objectives. So instead of learn a predictive model to maximize the predictive accuracy and later solve an optimization problem to maximize the decision quality. What we want to do is to learn a model to directly maximize the downstream decision quality so that we don't have this mismatch between two different objectives. So throughout my research, I've been working on different kinds of learning, including human behavior, adversarial machine learning, and also Gaussian process. In terms of planning, I also worked on a lot of optimization and reinforcement learning. And today I'm going to focus on the bottom part, the decision focused learning, which includes the following papers. Yeah, I won't go to too much detail about the math, but yeah, hopefully we can also learn something. So first, I'm gonna introduce more formally the idea of decision focused learning, in particular in the context of one-shot decision making problem. So as we mentioned before, this learning process and plus the optimization problem can be split into these two stages. The first stage is to use any kind of model, neural network, for example, to go from features to prediction. And our goal is to maximize the predictive accuracy. And this can be easily done by using a standard backpropagation or gradient descent algorithm, where we can define a loss function on an objective, for example, the predictive accuracy. And then we can just run gradient descent or gradient descent to loop through the entire data set and then update our model accordingly. This will finish the training process. And once we've done that, some example include like poaching hotspot prediction, like I mentioned before, and also some kind of cyber attack. We can also use features of each individual, let's say honeypots, to predict what's the attack risk of each individual honeypot or location, cyber locations. And for example, wildlife conservation, we can also predict the trafficking or smuggling risk of each individual routes, and then use that to determine where to allocate resources later. So I'm gonna use this as an example later. So one example here is, let's say we are given a smuggling or trafficking network, and where there are also features associated to each route. So what we can do is to look at the data set and then predict what's the poaching risk of each individual route. So for example, the darker the route is, the higher the risk is. And therefore, using this prediction and using the model that we just trained, we can later solve the planning problem now. So once we know this prediction, we know where are the poaching hotspots and where are the smuggling hotspots. We can assign the limited resources to intervene, to interdict those smuggling behavior, and therefore achieve the best performance of these interdictions. And as we mentioned before, what we really care here is actually the decision quality, the decision quality of our chosen policy. So in this case, what we really care is the performance of our assigned resources, assigned patrol or assigned intervention. And therefore, what we're gonna look at is just the performance of how these two interdiction, like how much smuggling interdiction we will be able to achieve here. And as we mentioned before, these two are different objectives. And one example here is that you can look at the prediction here. So suppose the prediction we are making here is not perfect. So somehow we make some incorrect prediction on the route down the blue line here. So the actual prediction should be there are more smuggling behavior in the end of this network. So the correct solution or correct assignment should be actually assigning those resources, limited resources, to the end of the network in order to achieve the best performance. But what we can see here is that this tiny bit of misprediction or tiny bit of predictive inaccuracy can lead to a significant change of the downstream decision. So actually, our decision goes from assigning resources to the blue lines to assigning resources in the red line, and which can lead to a significant change to the decision quality. So the main idea here we want to do is to mitigate this mismatch between objectives by using decision focusing. So instead of trying to maximize the predictive accuracy, what we want to do is to directly learn the model to maximize the downstream decision quality, which is the quality that we really care about, for example, the smuggling interdiction quality. And the idea is also simple. We can just use the same approach as we use in a standard learning approach. We can just do backpropagation. in this whole pipeline, we go from features to a neural network to a prediction. And once we got a prediction, and we can fit into a planning problem to get a decision. And once we had a decision, we can compute the decision quality associated to this decision. And what we can do here is to just use backpropagation, use gradient descent to directly backpropagate from the decision quality through the planning problem and through the prediction to update the neural network. By doing so, we can directly maximize, we can use gradient ascent to directly maximize the decision quality. But unfortunately, the main challenge here is that there's one component that's not directly differentiable, which is a planning component. So the neural network is just differentiable, but this planning problem is often formulated as an optimization problem. And therefore, differentiating to an optimization problem or planning problem is not intuitive, it's not trivial. But fortunately, Amos et al. In 2017 at ICNL, they published a paper to show showing that we can actually differentiate through an optimization problem by differentiating through the optimality condition, which I'm gonna briefly go through that later. And the main issue here, though, is that this whole process is extremely slow, and I'm also gonna show that to you as well. So the main idea that Amos et al. Proposed is that, so for example, we can formulate this planning problem as just an optimization problem. We can support when we can assume that the objective we want to optimize is a function f parameterized by a decision x and also the prediction theta, subject to some constraint as well. The main idea in order to differentiate through that is to first fit the prediction and then solve the optimization problem to find the optimal decision. So this is our forward pass of this neural network, of this machine learning pipeline. So in the forward pass, we need to solve the planning problem. In the backward pass, that's what we're gonna do next, which what we want to do is to differentiate through this planning problem, or differentiate through this optimization problem. In particular, what we want to do is to compute the derivative of the decision x star with respect to the prediction theta here, which if we can compute this, we will be able to backpropagate or differentiate through the derivative of the decisions and with respect to a prediction, and therefore we can backpropagate all the way to the neural network. And the idea proposed by Amos et al. Is that we can actually look at the KKT conditions of this optimization problem. If you don't know about KKT condition, you can think of that as like at the optimal solution, the gradient at the optimal solution must be 0. So there's no gradient at the optimal solution. So it's a necessary condition for optimality conditions. So therefore, for any optimal solution, x star must satisfy this KKT condition. So we have this equality KKT condition must equal to 0. By using this KKT condition, we can actually compute the total derivative of these KKT conditions. And then computing the total derivative of this KKT condition, we can further decompose the derivative into the following two terms. The first term will be the partial derivative with respect to x, the derivative of the KKT condition, and multiplied by another term, the derivative of x star with respect to the theta, the prediction here. The second term is just a partial derivative of theta. And by using implicit function theory, this actually was the first time that I used implicit function theory throughout my PhD. Well, I highly recommend that to you as well. So by using implicit function theory, we can actually compute the red term here, which is the derivative of x star with respect to theta, by solving the linear equation on the left bottom left, which actually gives us a closed form solution to the derivative that we want to compute. We might recall that we want to compute the derivative of optimal solution, optimal decision with respect to the predictions. So this closed form solution actually gives you that. And in particular, on the right-hand side, everything can be computed. For example, KKT condition is given, so you can just compute the derivative of a KKT condition, and also you can just easily invert the matrix. There are also some libraries, Python libraries implemented by Amos et al. You can just refer to QPTH and those CVXP1. Those are very nicely implemented. Well, but as I mentioned before, there are issues associated with this approach. And the issue is actually this approach is extremely slow. So recall that we need to, in the forward pass, we need to solve the planning problem. So actually we need to repeatedly solve this optimization problem, especially when this optimization becomes much more complicated. This forward pass will be much more expensive. In particular, in the backward pass, like I mentioned before, we need to go through this KKT condition and also compute a total derivative KKT condition. Although it's doable, but it can be also very expensive, especially when the dimensionality of this optimization problem becomes much larger. Then the solving this high dimensional KKT condition and also differentiating through that will become also much more expensive. So the main challenge is actually the scalability or the computation cost associated to this the decision focus learning pipeline. And this is just for one single gradient step. So for each individual gradient step, we need to go through the forward pass and then backpropagate by differentiating through the KKT condition. So you can imagine that will be extremely expensive. So here comes to our contribution, the first contribution. So in order to resolve the scalability issue in decision focus learning, the first idea is called surrogate decision focus learning. In particular, the main idea is, well, since we say solving and also differentiating through the original optimization problem can be very expensive, so we may not want to do that. So the main idea here is actually we can construct a new surrogate problem that's way cheaper than the original problem, that we can just go through, we can just use the surrogate, we can fit the prediction to the surrogate problem and then solve the surrogate problem and then later recover the decision. So by doing so, by using the surrogate problem, cheaper surrogate problem, we don't need to solve the original expensive optimization problem and also differentiate so that we can just use the surrogate problem as a surrogate. And this surrogate problem is also not just a random surrogate problem. We actually construct the surrogate problem from the original training problem. So the main idea of this surrogate problem is to use the original optimization problem, and then we reparameterize all the variable x in the original optimization problem by the product of p times y, where p is a surrogate parameter given fixed surrogate parameter here. And y is a much lower dimensional decision variable. So in the surrogate problem, we just substitute every x by p times y. And instead of optimizing through s, we just optimize through this lower dimensional y. As a result, you can see that the surrogate problem becomes a lower dimensional optimization problem because y is of much lower dimensional. Therefore, that's why it's easier and also cheaper to solve. One example of the previous smart learning domain is that instead of using like considering all the individual root as a decision variable because we may want to assign resources to each individual root, we may want to cluster or combine some roots together. So for example, if we want to assign resources, we will always assign resources to the blue region. Or if we want to assign resources, we will always assign resources to the yellow regions. By doing so, by clustering these decision variables, we will be able to get a lower dimensional representation of surrogate problem, so that in this case, we just need to optimize through four-dimensional problem instead of original higher dimensional problem. So as a result, since we use a lower dimensional surrogate or cheaper surrogate problem, the forward pass now becomes much cheaper because we just need to solve and optimize the lower dimensional problem. And so does the backward pass. Essentially, we just need to backpropagate through the surrogate problem. The surrogate problem is also of much lower dimensional, so the backward pass also becomes much cheaper. So both, we now are able to resolve both scalability issue in the forward pass and also in the backward pass. But on the other hand, this can actually destroy the solution quality, which is actually our final goal. So the main reason that can destroy the decision quality is because now the surrogate problem may not be the good surrogate problem. So for example, if our surrogate problem is not representative enough to represent the original optimization problem, it may not be able to represent the optimal solution in the original optimization problem, and therefore it could lead to poor performance. And the main issue here is actually coming from the surrogate parameter here we are using. Recall that we use this parameter P to reparameterize the high dimensional decision variable X by the lower dimensional decision variable Y. If this surrogate parameter is not good enough, is not representative enough, then our lower dimensional Y or lower dimensional space might not be able to capture the optimal solutions and lead to poor performance. So the main idea to resolve this the issue of decision quality is actually adding one more backward pass to update the surrogate parameter here. So instead of just backpropagating to a surrogate parameter to update the neural network, we can also add one more backward pass to update the surrogate parameter. Because previously we mentioned surrogate parameter can be poor because it not necessarily capture the optimal solution. But once we add this backward pass to the surrogate parameter, we will be able to jointly update the neural network and also the surrogate parameter so that the surrogate parameter can be gradually improved and therefore capture the optimality in the original problem. So this, by doing so, we are actually able to simultaneously achieve better performance, better decision quality, and also better scalability in both forward pass and also the backward pass. So one takeaway from this work is that dimension reduction actually improves the scalability in decision focus and especially dimension reduction in this optimization problem. And dimension reduction, unfortunately, is not enough. We also need to jointly learn the model and also the surrogate to learn how to do the dimension reduction. We cannot just use an arbitrary dimension reduction trick to improve the scalability. We need to use a better one. Okay, so that concludes the first approach to improve the scalability. I'm gonna introduce the second one, which is called block decision focusing. It's actually trying to address the same issue, trying to address the scalability issue of backward pass and also forward pass, but it's using a slightly different approach. So as we have seen before, this forward pass, if we just naively solve the training problem or the optimization problem repeatedly in the forward pass, and also backpropagate to that using KVD, that can be very expensive. So the main idea here in this work, in this block decision focusing, is to only backpropagate to a subset of decision variables. So in other words, we don't backpropagate to the entire KKD condition or the entire decision variables. We just backpropagate to a subset of KKD condition or subset of optimality conditions. So also using the previous example as an example, instead of backpropagating through all the decision variables, in this case will be all the edges in the network, we can just select a subset of decision variable or subset of edges, and then we just backpropagate to the optimality condition on these routes, on these edges, and to update the model. By doing so, we are able to largely improve the backward pass, the computation cost of backward pass. In particular, the original training problem can be just written as the high dimensional optimization problem, and the new version of the optimization problem, we can just look at the subset of decision variable here, which is denoted by X subscript C here, and this new decision variable is much lower dimensional, as we mentioned, similar to the previous surrogate approach, but using a different idea. But by using this subsampling or subset of decision variable, the idea of subset of decision variable, we will be able to improve the computation cost of the backpropagation. And therefore, it will resolve the computation cost of the backward pass, but unfortunately, this does not address the computation cost in the forward pass. In the forward pass, we still need to repeatedly solve this high dimensional optimization problem. But the good thing about this work is that this actually has some approximation guarantee, because now instead of backpropagating through the entire decision variable, we just sample some decision variables to backpropagate. We can actually build some approximation bound on the gradient that we computed from this subsampling approach. And therefore, this approach is actually in average a stochastic gradient descent of the original version of backpropagating through the entire decision variables. So although we cannot resolve the computation cost in the forward pass, but in this case, we are able to achieve approximation guarantee instead. This is by using a slightly different dimension reduction trick, different from the previous surrogate approach. So here's some experimental result related to the previous two works. So we test our algorithm, in particular two-stage approach, which is by learning a model to maximize the predictive accuracy, and then later solve the optimization problem. As we had shown before, this two-stage approach can have poor performance because it's optimizing the predictive accuracy, it's not optimizing the decision quality, which is the one that we really care. As you can see in the bottom here, we plot the regrade in terms of different methods, and regrade is a difference between our solution quality and the optimal solution quality, and therefore the lower the better. As you can see, that two-stage approach, which is the green bars here, is universally higher than all the other approaches. And the next approach is the naive decision-focused learning. So, which is by solving the optimization problem repeatedly and then propagating through the optimization using the KKT conditions. As we have shown before, it has a poor scalability. It can be extremely expensive in the forward pass and also in the backward pass, but it has a good performance. We can see that on the bottom left, it actually improved the regrade a little bit, but not too much. And the yellow one, which is the second one that I just introduced, the block sampling approach, which just differentiates to a subset of decision variables instead of all the decision variables. So as we have shown before, it has a better scalability because it can solve the computation cost in the backward pass. And it can also maintain good performance with guarantee. And lastly, we have the surrogate approach, which can achieve the best scalability because it can resolve both the scalability in the forward pass and also in the backward pass. In the performance-wise, it can also empirically achieve the best performance, although it doesn't have any guarantee load. And instead, beyond the smart gradient intervention problem, we also test this for algorithm, not the block version, on two other industry challenges, including movie recommendation and also portfolio optimization, where you can also see a similar trend between two-stage and decision focusing and also surrogate approach, where the surrogate approach is usually the best among three. And this is the first study on scalability issue of decision focusing. So previous decision focusing just not even look at the performance metric, but we also look at the scalability challenge associated to decision focusing and propose these two variants of decision focusing that can improve the scalability and also empirically improve the performance as well. Yeah, so that concludes the first part. And next, I'm gonna go to the second part of the decision focusing, which is related to sequential decision making. So far, everything we have mentioned is just a one-shot decision making problem, which is usually formulated as an optimization problem. As we have shown before, it can be just written as an optimization problem that trying to optimize an objective f of x theta subject to some constraints. But in reality, a lot of social challenges and industry challenges cannot be formulated as a one-shot optimization problem, or just an optimization problem. Most of the problem are sequential decision making. So that motivates the study of this work, which is what if the optimization problem or the planning problems becomes a sequential decision making, then can we still do decision focusing? So yeah, this is the main difference. Now the planning problem is no longer just a one-shot planning problem, it's a sequential planning, and therefore final decision is also not just one-shot decision. It becomes a sequential policy, which our final objective is the policy quality instead of just the predictive accuracy. So some examples of this sequential decision making would be, like, for example, if we want to plan patrol in the national park, trying to remove some snares in the national park. But if we do not know the snare placement and also what's the probability of seeing a snare or poaching in each location, our patrol policy may become a sequential policy, which is trying to look through each location in the national park and then get a sense of what's the risk also associated risk of dislocation, and simultaneously trying to remove as many snares as possible. So as you can see that it becomes a sequential planning problem that we have to determine whether there's a snare and also maintain the posteriority or the snare probability. And similarly, in healthcare service scheduling that I briefly touched base on, is this problem is that we need to sequentially schedule service calls to these models or beneficiary, trying to maximize the engagement with the healthcare service program. But unfortunately, we do not know whether these models will be engaging or not engaging. So we had to sequentially determine whether we should make a service call to call these models or this beneficiary, depending on the observation, whether they are currently engaging or not. So it also becomes a sequential planning program that is no longer just a one-shot decision making. We cannot just determine one decision and then execute that. And as we mentioned before, the standard approach, the standard learning approach, which is the two-stage approach, is trying to just learn the model and trying to maximize the predictive accuracy. In the bottom left of the the patrol planning problem, this prediction will be just a predictive model that can that's trying to predict the poaching risk or the snare placement risk of each individual location. But it doesn't capture the later the snare placement because poacher can come and also place snare at different time steps. So it doesn't capture that the sequential decision making part. And similarly, on the right-hand side, the healthcare service program, the prediction could be just the probability of dropping engagement of each individual model, but it also doesn't capture the sequential decision-making component instead. So our main question is whether we can also integrate this sequential planning problem to the learning pipeline and also achieve decision focusing by directly backpropagating all the way from the policy quality through the sequential planning to update the model. And therefore, the main question is whether we are able to directly learn a model to maximize the policy quality when there's a non-differential component sequential planning involved. Well, the answer is yes. And we actually use a similar idea as we used before as a KTD condition idea. So the main bottleneck here is the only non-differentiable component, which is a sequential planning problem here. And therefore, all we want to do is to, in order to backpropagate through this entire process, all we want to do is to just backpropagate through the sequential planning problem. In particular, if we want to, all we want to do to backpropagate this sequential planning problem is to actually compute the derivative of the optimal sequential policy here that we will be using eventually with respect to the prediction theta here. So all we want to do is to compute the derivative of pi star with respect to the theta. And we can use the same trick as we have seen before, like by looking at the optimality condition. Previously, we had a KDD condition in standard optimization problem. In this context, since we are working on sequential planning problem, so actually we had a slightly different optimality condition, which is called a policy optimality. As you can see here, the optimal policy must maximize the expected cumulative return. Otherwise, it would not be an optimal policy. So we actually have some kind of optimality condition here. And another way to express this policy optimality condition is that you can think of that as the necessary condition of this optimality condition, which is at the optimal solution, there should also be no gradient at the optimal solution. Otherwise, we will be able to improve this policy further and then violate the optimality condition. So we know that at the optimal solution pi star, there's no gradient. Therefore, we can just express this condition, necessary condition. The gradient must equals to 0. By using a similar trick as we have seen before, we can compute the total derivative of this automatic condition, this gradient equals to 0. And later, just apply chain rule and also decompose the gradient to derive the following linear equation. And as we have seen before, now the return, which is actually the derivative we want to compute, pops up. And all we need to do is to just solve this linear equation, and we will be able to get or compute the derivative that we want to compute. But on the other hand, it's also slightly different from the one-shot optimization problem, because now the expected cumulative return is not defined in closed form. So actually computing these two terms can be challenging now. Instead of using the KD condition that's given, now we had an implicitly defined expected cumulative return that we have to differentiate. But fortunately, there's also some literature in policy gradient theory. You might have heard of policy gradient theory in the literature of reinforcement learning. The idea of policy gradient theory is actually trying to compute the derivative of the expected cumulative return with respect to the policy pi here. So you can see that the derivative we want to compute is with respect to pi, which is policy. So we can actually just apply policy gradient theory to compute unbiased estimate of these two terms. We cannot get a closed form, but we can get an unbiased estimate, and therefore use an unbiased estimate of these two terms to compute the derivative, the return that we wanted to compute. So all this suggests that we are able to achieve decision focusing in sequential problems. So as we mentioned before, once we are able to differentiate through the sequential planning problem, which is essentially just computing this return, the derivative of pi star with respect to theta, we will be able to achieve decision focusing in sequential problem. So the answer is yes, there's also decision focusing when sequential problems involved. So here comes to the final topics related to decision focusing. And this is, before we dive into that, let me just briefly introduce some application of sequential planning problem of decision focusing. So this is exactly the same as the same application collaboration with ARMN, the NGO in India, where ARMN used automate messages to provide healthcare information to mothers in India. They try to use this automate message and use this health information to improve the overall maternal and child health. For example, you may want to suggest mothers to take some specific nutrition in order to prevent some preventative disease during their pregnancy. Well, but unfortunately, the challenge is that, well, mother may stop listening to the automate message because automate messages are just automate messages. It's very common for people to stop listening to automate messages. And the solution that they provide, this NGO provide, is actually that instead of just using automate messages, you can actually schedule actual human service code, schedule some healthcare workers to call this mother, and also hopefully by scheduling those service code, we can retain the engagement of these mothers with the healthcare program. So all we want to do right now is to find the optimal sequential policy that can retain the most engagement of these mothers, depending on their current state, whether they are listening or whether they are not listening to the automated messages. I also wanted to highlight that this is not a small problem. This is actually a large-scale problem that involves more than 20,000, more than 200,000 women involved in India, and also there are also around 7,000 healthcare workers involved trying to make those service calls. So this is not a small at all problem. We had to actually take the scalability issue seriously. And like we mentioned before, we can also fit this process into the pipeline we had before, where the features here are the demographic features. So mothers may have some demographic features. We can use those demographic features to predict their engagement behavior. So whether they transition from not listening to the code to listening to the code, or whether the other way around. Once we had those transition probability, we had the estimate of their engagement behavior, we can use those predictions to determine how we want to schedule the service code with this model in order to maximize the overall engagement performance. So we can see that there's an application, of this decision focused learning with sequential planning problem involved. As we mentioned before, two-stage approach, which is simple. We can just maximize the predictive accuracy by maximizing our predictive accuracy on the engagement prediction. That actually lead to very good performance. That actually lead to very good improvement in terms of compared to just randomly predicting and also randomly assign schedule a service code to models. So actually, this learning approach using this two-stage approach by maximizing the predictive accuracy can already achieve around 30% of improvement compared to random policy, which is shown by this Matt et al. At AAAI in AAAI 2022. And our question here will be, well, can decision focused learning just by changing the objective, changing the learning method, further improve the performance? Actually, the answer is yes, and it's surprisingly a lot. So by looking at the right objective to maximize, instead of just maximize predictive accuracy, we can maximize the final policy quality or final engagement performance. We can actually achieve similar improvement going from random to two-stage and also from two-stage to decision focused learning. Well, but unfortunately, like I mentioned, this problem is a large-scale problem that repeatedly solving the sequential planning problem can be extremely expensive, especially when there are 200,000 people involved in the program. And also backpropagating so that can be even more terrible. So as I mentioned, scalability issue is a major challenge, major bottleneck of this work. So that motivate the study of this approach. So instead of just considering this as just a standard sequential planning problem, this problem we actually formulated that as a variant of multi-unbounded problem, which is called restless multi-unbounded. And in restless multi-unbounded, there is some specific solution to restless multi-unbounded that we can solve that approximately. So instead of solving the sequential planning problem optimally, here we are just solving the sequential planning problem, specifically restless multi-unbounded problem approximately. And in particular, this approximate solution is called Pareto index policy. So instead of going through this expensive planning problem by solving that optimally, we go through this approximate solution, Pareto index planning, to define Pareto index and also use the top K solution to select the top K Pareto index to schedule a service code, and that would define our Pareto index policy. It turns out this Pareto index planning is much cheaper than the original planning problem. So we can actually solve this Pareto index planning more efficiently than the original planning problem, and so does the backward pass. We can also efficiently backpropagate through this Pareto index planning much faster than the original planning problem. So it turns out that by using this approximate solution, Pareto index planning, we are able to more efficiently solve and also backpropagate through the sequential planning problem. And then that resolve the scalability issue. So the main takeaway here is that we can actually leverage some domain-specific solution in the planning problem. In this context, that would be the restless multi-unbounded problem. And there's some approximate solution that we can use. It turns out that this approximate solution is more scalable and also much easier to differentiate to. And by using this approximate solution, we are able to achieve decision focusing in sequential planning problems. Yeah. So here's the performance in terms of engagement and also in terms of just the predictive accuracy. So you can see that on the right-hand side, as we have shown before, decision focusing can actually achieve much better performance, engagement performance than two-stage and also than random. And on the left-hand side, we can see that two-stage method, unsurprisingly, can achieve better predictive accuracy because two-stage approach is trying to maximize the predictive accuracy. So it's pretty reasonable for two-stage to achieve better predictive accuracy. And decision focusing, on the other hand, just achieves slightly worse predictive accuracy, but it doesn't differ too much. It turns out this small difference in terms of predictive accuracy can lead to a large difference in the engagement performance, which also justify our original motivation to study the mismatch between these two objectives. Apparently, there are mismatch between the predictive accuracy and also the final decision quality. And this work is, to our knowledge, is the first decision-focused learning on real work sequential planning problem with real application. That's much larger than the previous study, the one that we just introduced with theoretical results only. Yeah, and our next step is to actually deploy this approach, decision focusing into a real world problem with NGO in Amen. And in particular, yeah, like I mentioned, we are collaborating with Amen, and on the other hand, I'm also collaborating with some other NGO in Taiwan to try to use AI in environmental policy. So I just want to highlight without their helps and also their collaboration, it's impossible for us to achieve this. I'm gonna skip the final part, but we can come back to the data. But let me jump to the conclusions. Yeah. So in conclusion, I just wanted to say that decision focusing in the main idea of decision focusing is trying to address the important issue of this mismatch objectives. As we mentioned before, the predictive accuracy and also decision quality, these two are different objectives. So we should, if we care about the decision quality, we should directly maximize the decision quality. We should not just use the predictive accuracy as our objective. And that motivates the study of decision focusing, and also motivate the study of trying to differentiate into different kind of planning problem, including one-shot planning problem and also sequential planning problem. And on the other hand, decision focusing to some extent is also trying to incorporate prior knowledge or planning problems into your learning pipeline or the training pipeline, because we are now integrating the planning problem or the decision-making problem in the machine learning pipeline. So to some extent, we are integrating the prior knowledge of this planning problem to devise or to change how we backpropagate gradient and also how we update the machine learning model that we want to use. So this to some extent is trying to integrate prior knowledge into the machine learning pipeline. And there are also some works trying to just replace all the machine learning or replace all the neural network components by optimization layers, and hopefully optimization layers, differentiable optimization layers can be more representative and also can maintain more knowledge of optimization operations behavior, therefore it can solve more complex problem. But yeah, that's different. That's a different direction. No. And on the technical front, as we mentioned before, the differentiability of these planning problems is a major challenge for decision focusing. In order to achieve decision focusing, we need to differentiate through this planning problem. And actually achieving differentiability in different planning problems can have different solutions. Like we mentioned before, scalability is an issue, so that's something we need to resolve. And on the other hand, different planning problems can have different approximations. So we not necessarily always use the KDD conditions to compute a derivative. Sometimes we can use the specific solution for the planning problem and then just differentiate through that specific solution, some approximate solution or some other solution that can solve the planning problem. So adaptation to this different planning problem is also very an interesting direction in decision focusing that can simultaneously resolve the issue of scalability and also achieve good performance in this planning process as well. And yeah, I think with that, I would like to conclude here. And so please feel free to ask any question or send me a message if you have any questions. Yeah, thank you.
Yes, so thank you so much, Kai Wang, for the insightful tutorial session. So